union means or intersection means, and you guys knew the U and the inverted U part. So so if A is an event and A superscript C or AC is its complement, then the probability of A union A complement is 1. Now, what is A complement? A complement simply means anything that is not A. So we have an entire sample space, and in that sample space, anything that doesn't belong in A would become A complement. So, you know, we all know Venn diagrams. Do we know what that is?
Yeah. Okay. Circles.
Yes, 20 circles.
Oh.
I mean, does it have to be a circle? No, it could be something else. That looks like the flag of Japan if we shape it there. So that would be the entire sample space, and this is the set A. Everything that is not A would be A complement. So if all of this is A, what is A complement? The everything that's not shaded, so that will become A complement. So clearly, A and A complement are disjoint, right? So disjoint in the sense there is no overlap. Another phrase that we use to describe disjoint events. Well, if I look at A, then you're excluding all of A complements. And if you're looking at A complements, you are excluding all of A. So if you put them together simultaneously, they can't both exist at the same time. Either this would exist or that event would exist, but together they cannot. So one would exclude the existence of the other. So disjoint, we could also call it as mutually exclusive. So event A and its complement are always disjoint and they are mutually exclusive. That said, we want to find the union. What is A union A complement? Omega. Yeah. And what is the probability of omega? 1. Good. So if A is a subset of B, then the probability of A will be less than the probability of B. If they are equal, then the probabilities naturally must be the same because A and B are one and the same. You can show this easily using a Venn diagram. part is A. Now, what is a complement?
Plus whatever's in the little area around it.
So B plus whatever that's in that area.
Everything that could be at the top.
So how can we write probability of A? Well, probability of A, we could write it in a bunch of ways. A that overlaps with all of that that's around would be A complement, right? So whatever that's common with B union A complement would be the probability of A, right? So probability of A intersect all of those. And that would simply be distribute, and you have probability of A intersect A complement. I'm just distributing. What is the probability of A intersect A complement? Zero, because they can't happen at the same time. So probability of A intersect B, in this case, will simply be equal to probability of A. Now, how do we find the probability of B? That's the easy part. So again, we could start with the probability of A. So probability of B would be this part. And we know the rest of it is A complement. In other words, B union A complement, B intersect A complement. Yes? So all of that will be A complement in black. Do we agree? Yeah, give me 1 second. Go ahead.
Probability B is probability A union B, so that's definitely less than intersect.
Well, we haven't done the addition rule. That's why I'm doing it this way. So all of that would be A complement. So I want to find B. What would B be in terms of B and A complement? In other words, I want this part. What will that double shaded part be? Hence overlap. Go ahead.
I was going to say it's the probability of B minus the probability of A.
Okay, that's correct.
Or B intersects A complement.
B intersect A complement. So that would work too, but you know, I'm trying to kind of find or show that. So this part, I could say that part is simply whatever B is that overlaps with A complement, which is everything that's in black. So I could write probability of B as probability of A union B intersect A complement. Right? So this bit is A union B intersect A complement. Double crossed something production cost. Let's see if it's there. So we can write this as probability of A union B. What is the rule? The distributed set theory. If you distribute, what would you get?
Oh, I think, what is the rule? How's it go?
Plus
Yeah.
What is the
zero,
rule?
Plus what?
0,
0, which would be probability of
a intersection with a complement.
probability of A intersect A complement, and that would be 0. Let's see, what other ways could we address this? So using these two, we could actually come up with the addition rules, so probably I'll say this over here, but still. In terms of union, could I write it in a different way? A union the probability of B, which would be all of these, which would be the probability of A union. Could I use something else? Just, well, of course, B, but anything else involving A complement.
No.
How about B union A complement? Would that work? No, that's not going to work. What am I missing here?
The probability of A intersecting B.
But we did that already, right? Well, we'll do it that way. Sure. Probability of A plus the intersection of A and B, right? Which would be that part. B and A, the intersecting part. So that will be probability of A intersect B. And probability is a positive quantity, right? So it has to be between 0 and 1. It could be equal to 1. So naturally, this would mean probability of the less than or equal, greater than or equal to probability of A. The equal to part would apply if the A intersect B part is 0. You can flip it and write it another way, so probability of A is less than or equal to probability of B.
A intersect B, would that just be A? So probability of B is equal to probability A plus probability A.
If A intersect B equals,
Yeah,
Yeah,
it has to be because A is a subset of B.
yeah.
so the way I did it, yes, for this case, still, it has to be bigger than the probability of A, right?
Yeah.
Right, in this case, because I use the same thing, A is a subset of B. We could use a separate case. Let's see, over here. The 2 times the probability of A is still bigger than the probability of A. If I use the different case where I use this, and I have A and B, that would be A intersect B. Right. So what is the probability of B?
The cardinality of B over cardinality.
No, in terms of Venn diagram and in terms of set. So I want this part right here. Probability of B.
That's B without
A
B
B,
intersect B.
but B without what?
B without A intersect B.
B without A intersect B. In terms of A and B complement, could we write it in terms of A and B complement? Excuse me. In terms of A complement.
B intersect A complement.
B intersect A complement would be B, all of B.
That would be B without a little like
A
over.
intersect B is not part of A complement.
Come again?
A intersect B is A complement. It's not always A B without A.
Why are we making this way too hard? So let me see, probability of A, I could write it as probability of, excuse me, probability of B is probability of A, which is this part. Union, what is the remaining part?
B intersect A.
B intersects A complement. The rest of it is all A complement, so this would be B intersects A complement. You can also say B union A complement, right? Because we're including all of those to be B intersects A complement. Which will give us probability of A union B plus probability of A intersect A complement, which would be 1 in that case, right? No, 0. So this would be probability of A union B. That doesn't seem right.
Yeah, because at the start, so A union with anything else is gonna give you all of A, not B, right?
The Venn diagram is the subset, A is the subset of C.
So we're trying to find the probability of B. So probability of B would be all of this part, right?
Instead of A, shouldn't it be,
Union
shouldn't it be A intersect B?
A intersect B, right?
No, that, the part you just erased is fine, that should be A complement, so, because you're basically breaking it down into two parts. You're breaking it down into the part where A and B intersect, and the part where B is excluding A. So you have A intersect B, which includes both of it, and then you have B intersect A complement, which still includes what's in B without including that little sliver where they intersect each other. Then you have those two together, and that makes up the probability of B.
Again, this is very simple. Why are we making this very hard? So we want to find the probability of B, which would simply be B intersect A complement, definitely.
Union, B intersect A.
What?
Union, B intersect A complement, union, B intersect A.
B intersect
A,
complement and what?
union,
Union
B intersect A.
B intersect A, which would be that part. Isn't that what we did?
No.
No, it was A instead of A complement, A union. It was A instead of A intersect B.
Okay. Which would simply mean probability of A intersect B union B, which would be probability of A intersect B. Yes. And the other part plus probability of B intersect A complement. That's just probability of B. This is very simple. Let's try something else. What is probability of A? I could simply write it as the probability of B, which is all of that, yes. And then I subtract probability of A intersects B. Right?
No, that just gives you the part that is in B but not in A.
I think the problem is that the Venn diagram is just makes it so A is the one where it's going to be.
No, I want it to be the case that it is not a subset of. It happens. So we missed the part that A is a subset of B. Of course, there is another way to show this using unions. I don't know how the book is going to show this. I'm sure it's there. So we want to find the probability of A union B. In this case, we are going to consider that properly. So that would simply mean first I count the probability of A, which would be all of those. Yes. So probability of A. And I want to compute the probability of B also. So I'm going to find the probability of B. But when I do that, I double counted the part that was in the middle. Right? So I accounted for this part once already. Then I came back this way and I accounted for that part for the second time. So I'm double counting. So I have to get rid of one.
Exactly, intersect.
Minus A intersect. There we go. Now that is the addition one. So if they are disjoint, then A intersect B doesn't exist, right? It can't happen at the same time. So the probability of that would be 0, and probability of A union B would simply be equal to probability of A plus probability of B. So if I set B to be equal to the complement of A, and I could use the rule, probability of A union A complement will be equal to the probability of A plus the probability of A complement. And what is that part? 0, because they can't exist, so minus 0. What is the probability of A union? Okay, what is A union A complement? Omega. So we have probability of omega equals probability of A plus the probability of A complement. And what is that? 1. And this is what you would have read in an undergraduate textbook as the complementary, like probability of A plus the probability of A complement is equal to 1.
I think I figured out how to prove the thing you just heard.
How?
I figured out how to prove the thing you just heard.
Okay.
I think I just figured out how to prove the A probability A is less than the probability of B. But
How'd you do it? Using union?
I don't know. I just said that it's the probability of B.
Show it to that end of class.
You know what I'm thinking about. I will.
Yeah, we'll look at it. Okay, so I can extend this rule and take it to more than 2 events, let's say I'm going to use a different notation. Probability of A1 union A2 union A3. Now beyond this, it's going to be really hard for us to draw Venn diagrams. I'll just jump in and say this is what it is. We must have seen this too, or you should have, right? Now, that would be the probability of A, or A1. So, probability of A1 counts that part, and that part. Probability of A2 will count all of that, yes? But A1 counted this part. Now A2 is counting that part also. So we have to take away one part of A1 intersect A2. Does that make sense? So we will do that perhaps right here. A3 would count that part. So when we find that we would have counted this twice, so we will end up subtracting A1 intersect A3. However, did we have something else? 2 and 3. So A1, A2, A3, so 3, 6 and 7 times, yes. When we counted A2, we counted that part and that part. So A2 intersect A3 got counted once. When we found the probability of A3, we had A3 part, A2 intersect A3 again. So we have to take that away also. But finally, we counted and took it away. We counted and took it away. What did I take away? That central part right there. Yes.
Just to clarify, what you're subtracting, that's where the 2 groups are meeting, correct?
Yes.
Okay.
Yes.
The intersection part. So each time we counted that central part, we kept taking it away. So eventually this part needs to be added back in for the rule to be satisfied. So probability A1 intersect A2 intersect A3, and that would be that tiny little part. So same process like we did over here. Each time you count for A1, so A1's over there, and then you count that A1 intersect A2 intersect A3, and then you go over there, you'd have to subtract it out, add it back in, subtract it out. So when you finish that process, you would actually have one additional A1, yes.
So if we had 4 components, we could add the components themselves and take out the points, the areas where 2 of them intersect, and add in the areas where 3 of them intersect, and finally eliminate the areas where all.
Yes, that's exactly what I'm going to do.
Okay.
So suppose you had more than 3 events. Going to erase this part. Well, I'll do a problem too. This is what we call the inclusion-exclusion principle. I wouldn't put a problem, for k greater than 3. It's painful. Doable, but, painful. And we want to find the probability of I equals 1 to k a sub I. That would equal so sum of probabilities of AI. So you can see here, I had A1, A2, A3. I've had the union of A1, A2, and A3. I added all probabilities. So that would be the first sum. Yes. Now, every 2 intersection, I'll call it every 2 intersection. So that is a 2 intersection, 2 event intersection. So A1 intersect A2, A1 intersect A3, A2 intersect A3, right? So if you look at it, we can sort of order it and say, well, this is always less than that part. That is always less than that part. That is always less than that part. So we are going to sum them all and put a condition for I less than j, probability of AI intersect AJ. Yes, so that will be all 2 event intersections. What should the sign be? Minus.
Yes, so we go to k at the top of the sum.
Yeah, we just don't have to write it. We'll just say I less than k. Naturally, we go all the way up to k. If you want, you can put it in. What should the next sign be? Should it be positive or should it be negative? In our case, you look at the 3 event case, naturally, it was positive. But if you had more than 3 events, we would have done the exact same thing, right? We would have taken some, added some, taken some, added some from different events. So eventually you will see that this would be one term, you'd end up having another of this kind, but perhaps it would be 2, 3, 4, and then you would have 1, 2, 4, and so forth, and you would take every single combination. Regardless, that sum will satisfy I to be less than j to be less than k. So, well, I shouldn't use k. And because I used k already, AI intersect AJ intersect AN. So you add every 3 event intersections, and the next sign should be minus. After that, plus. After that, so it's going to keep on going. It becomes an alternating series. So the last one would be minus 1 raised n plus 1. If I have to satisfy that condition, probability of A1 intersect A2 intersect A3, what should go here? And all is said and done, what should the last term be? Pay close attention. First, we looked at individual events, A1, A2, A3. Then all 2 event intersections. Then all 3 event intersections. Then all 4 event intersections. Then all 5, I can keep on going. Yes,
It's the intersection of all the events.
intersection of all n events. Correct. So we have individual events, 2 event intersection, 3 event intersection, 4, 5, 6. Keep on going, and finally, we will have an intersection of all.
A question.
Yes.
Should be -1 to the k plus 1 now? Okay.
Good. Of course, you know, as I mentioned, if you have more than 3 events, things typically get very complicated. There are, you know, probability theory people who focus on things like this, but this has a name. It is called inclusion. Exclusion principle. Clear? Are we good? So as I mentioned in this class, we won't go past 2 or 3, or technically 3. We'll stop at 3. What would happen if all of those events are disjoint? Every single one of them. They're disjoint, you know, each other.
Intersection is equal to 0.
All of them would become 0, and we will simply have the sum of probabilities. That's what we call mutually exhaustive events, or exhaustively disjoint events, where every possible combination is disjoint, so eventually you simply have that. If we get that in real life, it would be very, very easy. But sometimes it does happen. Are we clear with this? Okay. When I do probability, probability related problems using counting, I'll do an example on this.